Okay, so let's have a look at examples of proof by induction. And we'll look at the process and how we solve these questions. So we're going straight into an example today. So example 1, we're going to prove by induction that the sum is r equals 1 up to n of r cubed. That gives me n squared bracket n plus 1 all squared divided by 4. Okay, so we're proving that the sum is r begins at 1 up to the value n of r cubed, would summate to n squared bracket n plus 1 squared over 4 for the value of n. Now that is something we're going to prove it's true, but that's actually a formula on your formula sheet when we looked at summations, okay? Therefore, we're actually going to show that this is actually, this is proven to be true, okay? So that's why it's on the formula sheet there, okay? Just one example. So, solution. We take our first value. So the first line of summation is when r equals 1, so we're going to let n equals 1 here, okay? And what we're going to do is we're going to look at what the left-hand side would equal, get a value for it, and then we'll get the right-hand side, get a value for it when n is 1, and then we'll hopefully have them both the same, therefore we prove that when n is 1, they both equal each other. Okay, so the left-hand side, so that's going to be the sum. N is now 1, so r begins up at 1 of r cubed. So if I put 1 into that, that's just 1 cubed. And 1 cubed is 1. So the left-hand side just gives me the value 1. Right-hand side, oh, no summation there, sorry. So when n is 1, okay, so that's going to equal 1 squared, 1 plus 1 all squared, over 4. Okay, 1 squared is just 1, so that's going to give me 2 squared, which is 4, 4 over 4, which is 1. Okay, so therefore, what we've done is we've said it's true for n equals 1. Okay, we've proven it's true for our starting off value. Okay, so that's the first step, and that'll be worth a mark in an exam paper if that came up. Okay, any questions at that stage here? Okay. So, next one. Okay, we are allowed to now assume true for a value of arbitrary value k. Okay, so n equals k. We're going to assume that what we get on the left-hand side and right-hand side is true here. So that means that what I'm saying is true is that the sum of r equals 1 up to k now of r cubed, well, that would equal k squared, k plus 1 all squared divided by 4. Okay, so we're allowed to assume that that is true for a value k. What I want to do now is try and prove that it'd be true for the next step. Okay, because if it's always true for the next step, then it's going to be true for any next number, therefore we can prove it for all values. Okay, so we're going to let n equals the next one, which will be k plus 1. Okay, now what we want to prove now, okay, so we want to prove that the sum is r equals 1 of r cubed up to k plus 1 now. What we want to prove is that on the right hand side that's going to give me k plus 1 all squared, k plus 1 all squared over 4. Okay, and I can just tidy that up, which gives me k plus 1 all squared, k plus 2 squared, all over 4. So if I can prove that that summation on the left-hand side would give me this on the right-hand side, therefore I've proven it's true for k plus 1. Okay, the next step. Alright, so it's always a good idea to write down what we want so that you can see what you're driving to. Okay, you can see what the end game or the end goal is here with this question. Alright, okay with that? So you also get a mark for writing out this statement as well, okay? You're assuming, or you're allowed to assume, sorry, and then say what you want to prove next time round. Okay? So what we'll do is we'll start up with the left hand side. So it's going to be the sum k plus 1, r equals 1 of r cubed. Now I'm going to split that summation up again. Okay, so I'm going to split that up so that I'm going to sum up the first k terms of r equals 1 r cubed. And then I'm going to add the k plus 1 term onto it. Now the k plus 1 term would be if I put k plus 1 into my r here, so it's going to be k plus 1 all cubed. Okay, so that's how I've split up that summation there. Okay, so that summation up to k plus 1 is the same as me summing up the first k values and then adding the k plus 1 value onto it. You okay with that step there? Yep, okay. Now remember, we're allowed to assume what this first thing was. So I'm going to use what I assumed to swap out for that first summation there. So that's going to be k squared, k plus 1 all squared, over 4, plus k plus 1 cubed. Okay. Okay, you okay with that? So what I'm going to do now is I'm going to want to get this as a denominator over 4 to combine them, yeah? Okay, so I'm going to have k squared, k plus 1, all squared, so I should say, plus k plus 1 cubed, multiplied by 4 over 4. Okay, so that way I've now got my denominators the same. I'll be able to combine them when I want to, okay? You understand that next step? Because I was just manipulating that last term there, yeah? Okay. So, if we think about our end game, what my end game, I want to get a k plus 1 and I want to get a 4, because that's what I've only got a k plus 2 yet. So what I'm going to do is, I'm going to take a common factor out of k plus 1 squared over 4. Both terms will have that. And what I'm left with will be k squared from the first term. Then I'm going to have 4 times just one of the brackets k plus 1. So I took 2 of the brackets out with that common factor. Okay. You okay with what I've done there, yeah? What my common factor's been? Okay. And if I tidy this up, then I'm going to get k squared plus 4k plus 4, okay, which is a trinomial. And that trinomial factorises as k plus 2 multiplied by k plus 2, so I've got k plus 2 squared. Okay, which is now me got what my right hand side is going to be, which is k plus 1 squared multiplied by k plus 2 squared, all over 4, which equaled what my right hand side I wanted to prove. Okay, so I started off with the left hand side and I managed to prove that I get the same thing as the right hand side all the way down there. Therefore, true for n equals k plus 1. Okay, so that's really important for us, because what that's allowed us to do is say, right, if we know the first thing's true, because we're assuming that it was true for k, arbitrary value, then we've proved that the next one's always true. So therefore, because we started off with n equals 1 being true, then because I've proved for the next one it's always true, therefore that'll be true for n equals 2. Okay, and if it's true for n equals 2, then it is true for n equals 3. And you can see, etc. It would just go on and on and on. Therefore, true for all values of n by induction. Okay. Are we okay with that example there? Right. So again, there was a fair bit of manipulation regarding the algebraic terms there to get what I wanted to get to, but the key thing is the process remained the same as what we were discussing. Yeah, and if you learn the process, you can then begin these questions and get there. Okay, they are quite tricky. Okay, but it's the process. The more practice you get, the more you spot what you're trying to look out for, and then you can see what things you need to take out as common factors. Okay, we'll look at a couple of different types of questions to show you they're not all summations, but summations are a vast amount of the examples that you would see in past papers. Okay, but not them all, definitely not them all. So we'll look at a second example. Example 2, prove by induction that n cubed plus 2 to the n is divisible by 3 for all values of n greater or equal than 1 and n's in the set of natural numbers there. Okay, so that's just a bit of notation there. That upside down sort of A looking thing, it means for all. Okay, so for all values of n greater than 1, we want to prove that n cubed plus 2n is divisible by 3 when n is natural numbers. Okay, like 1, 2, 3, 4, okay, no decimals, nothing like that. Okay. So you can see it's a totally different looking type of question, isn't it? Yeah. However, this clue here, this bit here, does tell us where our starting off point is. So our first one's going to be is we're going to prove that it's true, or hope it's true, when n is 1, our starting off value. Okay, so that's going to be the first step here. Okay, so we're going to let n equals 1. So the left hand side, well, there's only really one side here, so I don't really need that, but it's maybe just good notation to keep a hold of. Okay, left hand side, if I put 1 into that, that's going to equal 1 cubed plus 2 lots of 1. I'm just putting 1 into there. That's 1 plus 2, which is 3, which is divisible by 3. Okay, therefore, it's true for n equals 1. Okay, so my first step, shouldn't be too many problems with that bit there. Okay, so we're going to assume now, true again for some value n equals k. Okay, therefore, if I go to the left hand side, then that's going to be k cubed plus 2 lots of k. Okay, if I put k into that function. If we don't assume this is divisible by 3, okay, we'll assume at this stage. Therefore, how we would write that, if it's divisible by 3, then it means it's 3 lots of something. Okay, and we're just going to have that as m for some value m. Okay. Okay, so if k cubed plus 2k equals some sort of value for n multiplied by 3, then it means it's divisible by 3. Okay, so we're just writing, that's a way to just write it, divisible by 3. Okay, so we'll now let n equals k plus 1. So what we want to show here is that if we put k plus 1 into this, that we're also getting something divisible by 3. Okay, so what we want is that k plus 1 cubed plus 2 lots of k plus 1. Well, we want to prove that that's also something divisible by m, so we'll call it n. Okay, we'll sort of show that's divisible by some value. Oh, n's maybe a bad number letter to use, folks, because we've already used n in a question. I'll change that. What we'll do is we'll maybe call it p. Okay, I was a bit careless of me. Okay, because we already use n in a question. Right, so that's what we want to prove. So we're going to start off with k plus 1 cubed plus 2 lots of k plus 1. Okay. Now, if I multiply all this out, then I'm going to get k cubed. Remember, you actually know the quick way to multiply this out. You've got the binomial theorem that could actually help you with that. If you remember Pascal's triangle, they would tell you the constants that you would get on it. So the third row would be 1, so it would be 1 lot of k cubed, then it would be 3 lots of k squared, plus 3 lots of k plus 1. So that can be multiplied out of that first bracket. Okay, plus 2k plus 2. Okay, so if I multiply out that second bracket. Okay, if I can then tidy up what I've got here. Okay, but again, I can remember what I'm trying to use. I'm trying to get. I'm trying to use the fact that I can assume that this was true, isn't it? That was always the sort of theory behind this. I want to use this to help me prove that this bit's here. So what I'm going to do is, you can see I've got a k cubed and I've got a 2k as part of my question here so far. I'm going to put all that to the front because I'm going to have them combined like that, so I can say that this bit here would equal 3 lots of n, whatever n was. Okay, so I'm going to have k cubed plus 2 lots of k, so I'll put that 2k just after the k cubed. Then what I'd have left is 3k squared plus 3k plus 3. Okay, so it's got all the rest of the terms after that. Okay. So k cubed plus 2k, well, I know from the assumption stage that is going to be the value 3m. Okay. Then here, you'll notice that all my other terms here are also divisible by 3. Yeah? So I can go like that. Okay, so I'm just doing a common factor of the last 3 terms. And if I take my common factor of 3 out of both things, I've got that there. Okay, 3 lots of n plus k squared plus k plus 1. But the main thing is I've actually proven what I need to prove now, because what I've proved is that this thing here, no matter what the value of m is, and k is here, right, okay, it is divisible by 3. There's a common factor of 3 at the front. Therefore, I can just relabel all that as, say, a p value, okay, which is what I wanted to prove, okay. It was 3 times something, okay, 3 times p, okay, for some value p. Therefore, true for n equals k plus 1. Okay. And again, write our statements at the end. So, as it was true for n equals 1, therefore it would be true for n equals 2, because we proved the next step. True for n equals 2, therefore true for n equals 3, etc. So true for all values of n. So true for all values of n by induction. Are we okay with that one? Yeah? Any questions on that one there? No? Okay.